So hello. I think the last part that I gave on stability was a bit confusing. So I will try to repeat the stability issue. So certainly stability issue is important. It's probably not that, you will not encounter it that much in ordinary differential equations because the usual practice is that you use some routines which are already given. So they are stable. At the same time, if you create a method or that issue may be important, that issue was important for these routines, of course. At the same time, the stability equation, it extends also to the numerical schemes for partial differential equations, which you study in this. It's usually special. In IMPA, it's a separate course. So it's numerical analysis for partial differential equations, and there it's become a very major issue because stability is important. So I will just try to go through the whole this numerical ordinary differential equations topic and give repeating this stability equation. Certainly we don't go into the detail because there's no time, but just so what you should remember are two things: is that first is that it exists, so the method can be stable even if you make it high order, even if you create a high order scheme which approximate each step up to a certain power of h. So it's the step itself is accurate. The full scheme may not work. There's one thing, and the second is that what is the reason? And the reason is just really stability theory, which is stability theory for dynamical systems, and at the end it has to do with the spectrum of certain problems. So that's as usual stability. One of the ways how you study stability is through the spectrum for the eigenvalues. So let's just do this again. So first let's remember that there is so what we did is there were two methods. So the single step method, and there were multiple steps. So it was k step, right? So see how it. The multi-step. The name states for itself. So the single step, it was. So in both cases we study the same equation. So the derivative is a function of time and y, and also we have initial condition. So how to solve this initial value problem? Single step, it's solving the problem by taking the initial step, right? So this is y0. So just way around. So you take y0, and then you take y, then you iterate the equation that y at point k plus 1 is yk plus h, some function of time, position, and h. So here, and that times is t0 plus, so what was the interval, plus k over n steps by time interval. So this is more or less the idea. So essentially what you do is that taking time state, so you start with certain time at certain position, and then we want to find a solution. And what we do is we put, so we want to find a solution at certain time. So this is t0 plus t. And then we split this interval into the equal steps of size h, and then approximate each point, which is probably something a little bit different, but approximate each point by yk. So this is yk, and the other point is y at time tk. So this is the scheme, which is a single step. So the idea is that in a single step, the only information you use is what was in the previous step. Still, you can make some more calculation inside this interval, but the input is the previous step, just one. So the major representative of this single step method is Runge-Kutta. So this all Runge-Kutta methods is a single step method, so they only use the previous step. So now multi-step is a different method, and essentially the philosophy is that in a single step you only use previous position. But this is a kind of very small amount of information that you already have, because you have second position back, third position, fourth position. So you have many positions, other positions back in time, which also bring information about the function. Because if you have one position in time, you know more or less where is your solution. If you have two previous positions, you know more or less, you can approximate position and derivative. You have three positions, you can approximate second derivative. So it means that if you use many previous steps, you can create a high order method without making extra computations, because the computations were already done. So this is multi-step method, and it was formulated. So the general formulation is that you find a new position by having the previous states and functions f computed the previous state. So the general formula that is usually used is that it's a linear combination of the positions. So it's k step. So alpha k y j plus k plus alpha k minus 1 y j plus k minus 1 minus, no? Yeah. J, okay. This is equal to functions, and this is with betas, no? So time step, and then beta k, j plus k, beta j, where f j is the function computed at time and position. So you see, you use k plus 1 points. So you use k in previous points in order to compute the new one. So this is a new position that you want to compute, and the others is that what you already have. Right? So this is all you have, and in principle, the new position. What you have is 0. And in principle, you also, the new position, the unknown variable can enter in this function f. So if this term is non-zero, then it's implicit problem, because you need to solve a nonlinear equation with respect to the new variable. If it's 0, then it's explicit. Right? So that's an idea of multi-step method. So idea of multi-step method is that you create high-order scheme with just one computation of the new function. So the rest is already computed. So it's certainly better because, on one side, no? It's better because here, in order to have a high order scheme, you need to compute it many functions. And here, if you want high order scheme, you just use what was already computed. So that's different. So for this certainly single step method is in a sense a particular case of multi-step when k is 1. Only in that case this will be f. So this is essentially a version of the kind of species of the Euler method, no? Euler or some improved Euler. So multi-single step is not exactly the K1 case, it's a bit more elaborate version. Anyway, so we had the analysis of single-step method showing that it converges. So single-step method is good. So you can always use and it will converge. So the multi-step method can be unstable. And this is what we are going to study. So there was a very simple scheme, but now let's just make one more example. So in order to see how it doesn't work. So stability. So here I took another book which is in the references of the course. So it's Bullish and Stern. Introduction to numerical analysis. Okay, so consider the example. So let's just make one example of a multi-step method which shows you how everything works. What happens? So consider the multi-step method with two steps. So it means that whenever you want to compute any value here, you use two previous steps. Use two previous steps. And also we will consider explicit version. So explicit. So what it is? So just k equal 2. So we have yj plus 2. So let's already put coefficient 1 here. All coefficients are up to multiplication by constant, right? So just we can put 1 here. So it will be plus a1. It's alpha there, no? Okay. J. And then it's h. Beta 1, g plus 1, and g. So you see, I removed this term, so it's not explicit. So it will become explicit. So essentially, if you want to compute the new term, you already have this number, and already computed f's. So you just put it on the left-hand side to compute. It's direct, simple computation. Okay, so we need coefficients, right? We need what? Alpha 1, alpha 0, beta 1, and beta 0. So 4 coefficients. With 4 coefficients, so we will see what we will do. We will expand it in a Taylor series and just use coefficients in order to compensate the lowest order terms. So the 0 order term, first order term, second order term, third order terms, as much as we can. And it's clear that we can compensate with 4 coefficients. We can expect to compensate 4 first terms, so this will be third order method. So this is expectation, because up to the third order term, you can compensate everything. We expect. So now let's do it. So discretization error. Discretization error. So discretization error is what? What is the error of this equality in this equality if you substitute exact values at the place of the computed? Right? So this is how you compute. So what is so you substitute yj by y at time j, so by exact values. So yj is a computed value, y at j is exact value. So when we substitute, so what will be then an error of one step? So what it means, so this is, so it doesn't matter in which place we do, so we just put tj, substitute, write it as a t, so this at j plus 2 is a value at time t plus 2h, right? So plus 2 means plus 2 time steps. This will be t plus h. This is t. This is equal h. Beta 1. So now f. So let's fj we substitute by f at time tj and at the correct point, right? And this is by definition derivative. Right? So this will be beta 1 by derivative at the next step, and this will be beta 0 by derivative at the original. So this is a relation plus this plus some error that we want to find. So order of this error, which is usually OH with some power, say, R. So this is giving us the, this determines R plus 1. No? This determines an order of the method. Okay, so in order to define, so we expand everything in Taylor. And we have to expand it up to the fourth order terms, right? Because we expect that up to fourth order terms, we have enough unknowns to make a compensation. So we do it up to fourth order terms. So the first term, it's yt plus y dot. So all derivatives now will be at time t. So y dot h to h plus y dot double dot to h square over 2 plus y dot to h cube over 6 plus next term. So this is the first term. The second term will be alpha 1 yt plus y dot h plus y double dot h square over 2 triple dot 6. I will not write O because it's all here. Then plus alpha 0 y of t. And then this term. So this is h. Now, already one h is outside. So we expand only up to third order terms, second order terms, right? So 1h is already here. So it will be beta 1 y dot at time t, everything at time t. Now plus y double dot h plus y triple dot h square over 2. Right? So the correction is still here because it's OH free by h, so it enters here. And then plus beta 0 y dot t. Okay. So now we get the third order method if everything except for this term, everything cancels except for this term. So we have to cancel all the terms, and canceling all the terms is just collecting the checking the coefficients that multiply different derivatives vanish. So the coefficient that multiply y is what? 1 from here, alpha 1 from here, alpha 0 from there, equals 0. So this will cancel the terms which multiply y. Then the terms that multiply y dot, it's here to h, no, without h, y dot h, right? So plus just 2. Then alpha 1 from here. There is nothing, and here it's beta 1. No. First of all, it's on the other side, so it's minus, right? So let's write it as it is. So equal beta 1 here and beta 0 there. That's correct. And then the next term will be y double dot t h square. So first is here, it's 4h squared by 2, so it's still 2. Here it's h alpha over 2. This is beta 1. There is nothing else. Correct. And then the third order. This is how much? It's 8 by 6, which is 4 by 3. Third. Then this is by 6. Alpha 1 by 6. And then we have this beta 1 by 2. So linear system of 4 equations with respect to 4 unknowns. That I will not just solve, just let's give an answer. So it's, if it's non-singular, if the determinant is non-singular, it has a single unique solution, which is the case. So if you just make this, apply any method, as we did it from the beginning, so you find a solution. So alpha 1 is 4. Alpha 0 is minus 5. Beta 1 is 4 as well. Beta 0, 2. Yeah. Looks like works. So, as you see, we're actually completely restricted. So, we're just telling that it's a second order method in explicit form, coefficients are already given. Explicit form, and we choose the coefficients so that we get highest order method possible. This is the only way. So the method is yj plus 2 plus 4 yj plus 1 minus 5 yj equal h. Let's make it complete. F as t j plus 1 y j plus 1 plus 2 tj yj. So this is the second order, two-step. So it's two-step, third order scheme. So the error has in a single step, the error that you get is H4, which is supposedly very good. You just take H. So if you take H equal, for example, 0.01, right? So a single step gives error is H4. So this is 10 minus 8. So very, very nice. So just giving rather big step, 0.01, you get huge, expect very, very high accuracy. So let's see how it works. So let's solve the initial value problem. Y dot equal minus y, initial condition 1. So this is linear system. So why we do it is this is a theoretical example. We will do it because we can just make an explicit study of the whole problem for this example. Just make it direct computation. So we know that what is exact solution. So exact solution. So exact solution is y of t equal exponent minus time. So that's. So now let's find it numerically by hand. So let's apply. We apply this scheme. Two-step method. So two-step method is that instead of function, you put minus y. So two-step method gives you this. Let's just write it again. J plus 2 plus 4 yj plus 1 minus 5 yj equal h. So it's function is now just minus y. Minus 4 yj plus 1 minus 2 yj. Put it everything to the left hand side, and then you get yj plus 2 plus 4 minus, so it's 4, 1 minus h plus yj plus 1 plus minus 5 plus 2 to h yj 0. So that's a linear system. So it's a linear equation. So linear equation gives you next step if you know the two previous steps. So direct calculation. And since it's a linear system, in principle, we know how to solve them in general. So this, so in order to solve this system in general, so you need to find two particular solutions. Yeah? Because if you just have two initial states like y1, y0, you know all other states, right? So it means that if you have two particular solutions which are different, linear combination of these solutions will be a general solution. So the particular solution can be taken in the form, so yj, you can just take it as a power law. Lambda j, so we need to find lambda. So when you, and you can even put, okay, lambda j. So put it in. So it will be lambda j plus 2 plus 4 1 plus h y lambda j plus 1 lambda j equals 0. Cancel lambda j, and then you get lambda square plus 4 1 plus h lambda minus 5 plus 2h equals 0, which is usually called characteristic equation. Characteristic equation, and lambda is meaning of eigenvalue in that case. So that's essentially, and all values of all the solutions is what is called spectrum. So this is just like in the stability theory in any other field. So essentially, for differential equation and finite difference equations, like in dynamical systems. Okay, so quadratic equations. So we can solve it. So solution is, it's a lambda. Now remember, so you take half of the first coefficient, 2 plus 2h, and plus minus. So you take square of the half of the first minus the second. Yeah? So it's 2 plus 2h square minus the second, so it would be plus 5 minus 2h. Okay, this is 2 plus 2h. It will be 4, 5, 9. 8, 2 plus 2 plus 8 minus 2, 6 square. Let's put 3 outside. Like this. So I put it 3 outside because remember that h is small. So our interest will be in verifying that method is convergent. Convergence of the method is when you take smaller and smaller step. So h is small, so our interest is just in understanding what happens when h is small. Well, that's not so crucial because we have form of any h, but just it is we will need this formula. So when h is small, you can take expansion. So it will be 2 plus 2h plus minus 3. So how many terms we need? We just need 1 term. Yeah. So 1 plus 1/2 of this, right? So this is not what I meant, right? So it's 2, 3. No. You do not follow. So just take Taylor expansion of the square root because this is small, this is small. So that will be plus h over 3. Like this. So we have 2 eigenvalues, 2 roots. One, you take it with minus, right? So you take it, no, a bit confused. First of all, we forgot minus here because this term has to be taken with a minus, right? Nobody remembers how to solve.
Okay.
So we're taking with the plus will be 1 plus h, right? Correct. It should be minus. Because it was minus. What is the trouble? Okay. Minus. That would be plus. Okay. You should verify what I do. But anyway, it should be, if you take plus, so then, no, this is correct. So when you take plus, so it gives you plus h, but minus 2h. So okay now, correct. Okay, so that I copied it in the wrong way. So in lambda 2 is when you take minus, no, this was with minus, so this will be with plus. So plus, no, it was with plus, now with minus is minus 5. So this will be minus h and minus 2h, minus 3h. Yeah. So we have two independent solutions. So the general solution you can take yj. Just as a linear combination, one will be with one coefficient a. So alpha u, so we take a lambda 1 j plus b lambda 2 j. So this is general solution because they are different and with they're independent, and by choosing a and b, you can satisfy arbitrary initial conditions. So for any 2 points, y1, y0, you can, we will see that we find a and b, and then all the other y's are given by this formula. So this gives a general solution for our system. So this is good. So it's exactly what remains. So it remains to find a and b. So the a and b are determined by initial conditions, so y0, y1. Yeah? Practically, you find y0 is given, its initial point. y1 you find by any method. So it's just single point, so you just use, for example, Runge-Kutta high order in order to find y1. So we're with a theoretical example. So we can just take two, which we can just take best choice possible. So we just take exact values. So we take y0. So we take y0 to be 1, as it, and y1. Let's assume that we have a perfect method to compute y1. So we just take it exactly from exact solution. So that's it. So now what we have? So we have that y0 is a lambda 1 0 plus b lambda 2 0, right? So which is just a plus b, and it should be 1. So this is first equation, and then the second equation is a lambda 1 plus b lambda 2 should be this exponent. So this gives you a and b. So what you do, so how you compute a, you multiply this by lambda 1, lambda 2, and subtract. This cancel b, and then it gives you a. So a will be lambda 2 minus e minus h And then it will be divided by lambda 2 plus lambda 1. So this is A, and B is just the same way. So you multiply this by lambda 1 and subtract. This will be the same thing, but inversed. So this is minus. Okay, so we have A and B. And next, next what is important is that now what you can do is now you can expand it in H again. Right, so this is H is small, so if you substitute lambda 1, lambda 2, which we have, and make Taylor expansion, which I will not do, so you will find that A is say lambda, you see the first order term is what? So lambda 2, the first order term is minus 5, this gives 1, so minus 5 minus 1, minus 6, and here will be minus 5 minus lambda 1, which is 1, so minus 6. So its first order term is 1. And the rest does not matter. So actually, we already know that the first order term is 1. And here is worse, because here, in order to compute it, we need to take more terms here. And what you will see is that actually several terms will cancel here from the. So essentially, so you can check by expanding in a higher order series. So it's actually, this is actually very small. This will be minus H4. 2, 1, 6. So H5. So you need to expand it better in order to have the correct numerator. So what you can see is that we have two terms. One, essentially, it's this is big because it's proportional. The coefficient is essentially 1, and this is in principle very small because B is H4. So now let's compute. So Yj is 1 plus O H by lambda 1, which is 1 O minus H J plus minus H4 to 1, 6 by this minus 5. And actually, this term does not important, so it's not. So let's just take J. Okay, so this is up to highest order terms. And now compute. So compute y at the final point, t0 plus t. So which should be yn, right? So n steps. So remember that h is t over n, right? And in this case, so we took j equal n. So last step. Last point. So if we make the whole computation until the last point, which is at this time, so what will be the result? So we just compute this expression at the last point. So what we have is, so yn is 1 plus h. 1 minus h is this. in the power n. And the next term is, it's minus h over h4 216, and this 1 plus h, and then this minus 5 n. No, it's, I will, let's write it here. Let's put it in compact form here. Plus h4 216 h. So this is h squared. Let's just keep it as it was. Okay, good. So what do we have? So this is remains as h goes. So now we consider h small. So what happens with h small? So this goes to 1. Yeah. And this h small means, so essentially we take not h small, we take we want to compute more and more accurately, which means that we take more and more steps, n goes to infinity, which means that h goes to 0. Right? So this is a limit. So this goes to 1, and here the t capital is fixed. So this is time at which we want to compute. And this is 1 over n, so this is exponent. So this gives you exponent minus t. T0 is 0. So this is exactly solution. Exact solution that we want. So you see that the first term, as h goes, and if you take more and more steps, it converges to exact solution. And then there is the second term. And here, what it is, so I forgot that it is, I have to open h. So h is t over n squared. So 216 and 4. So what we get here, so this is 1, and then it will be t4 over 2016. This is constant. And then this n minus 4 at minus 5n. And this is a trouble, because if n is large, so this is minus 4, it makes it small. But this is exponential. So this always wins. So this explodes. This explodes. So you see, there are two terms. One term converges to exact solution as you make it finer and finer steps, and the second term explodes. So this is instability. So you see, it explodes when the exponential terms start to win the first one, and it always wins. So exactly if you make explicit computations with, for example, so if you take h to be 0.01 and compute solution at time 1, so what you get numerically is that the last point will be something of order 10 power 60. It's not exponent minus 1, but it will be a huge number. And this will be a huge number because essentially everything is here. So this is instability. So we see that we started with good intentions. We took two previous points, general scheme, made it the best possible coefficients that make it high order. And the result is absolutely bad. So we do not converge. Let's make a short break, and then I will explain just idea of how the analysis, numeric analysis is done, which leads you to the stable method.
Ok. Então foi claro, né? Eu espero que foi. So how we proceed in general? So in general, our method is in general. In general, our k-step method. So k-step method, let's just write it again. So j plus k plus a k minus 1 y g plus k minus 1 plus e 0. It's alpha, no? It was alpha. Yj equal h, then this, the whole stuff. So it was beta k. So what happens with this method? So if we study stability, again, so let's, so the procedure, in fact, it turns out that instability is actually fully determined by the left-hand side. So what amplifies the error is just what stays on the left, and what stays on the right is less important. So first, let us just take this 0, right? Take this 0 because just at the first place, the method should work when the function is 0. Function is 0, it means that it should give at least, if f is 0, it's constant solution. So at least constant solution you have to get. So the stability analysis, we start with this, just with the equation, the linear part. So the left-hand side part. So y j plus k for k minus 1, j plus k minus 1. Zero. And again, it's a linear system with constant coefficients. So if we have k independent solutions, we have a solution. So we look for the particular solution. Particular solution. So solution is just the same form, the power law. Lambda j. You put it inside, cancel lambda j, and then you get characteristic equation. So you cancel lambda j for each term. So what remains is lambda k plus alpha k minus 1 lambda k minus 1. And so on until so lambda 1 alpha 1 lambda plus alpha 0. Polynomial of order of degree k. So it gives you, in principle, it gives you k roots, which can be complex, so real or complex. And counting multiplicities. So the same root can appear several times. So if you count them correctly, this is k roots. So now, if these roots, which we have k of them, right, are distinct if all of them different, so then you have k different solutions. That means that the general solution is a linear combination. For any coefficients. So taking arbitrary coefficients, you form a general solution. In general, so remember, so they're distinct, but they can be real and complex. So if so this gives actually a complex solution. Complex general solution with the complex coefficients if some lambdas are complex. But if it's a complex solution, but this is a linear system with real coefficients, which means that the real part of for a real solution, you just take a real part, right? So if you take real part of this, it's also solution. And if it was general solution in complex space, it's automatically general solution in real space. So, but technically, what you should do if there are complex roots, then for the complex conjugate roots, you take complex conjugate prefactors. Then you cancel imaginary part, but it's the same as just taking an imaginary part of the full, or real part of the full expression. So this is a general solution in the case of distinct lambdas, and if all lambdas has absolute value smaller than 1, right? So what you have is that, and remember that what is J? J is time divided by time at which you want to compute divided by number of steps, right? Or divided by no. Divided by h, by the time step. And usually we want h take small and small. Yeah? So J, it means that J goes to infinity. So in this case, Yj goes to 0 as h goes to 0, right? Because J is increasing, doesn't matter what are the coefficients, you look and check that you get convergence. Essentially, it's a bit more sophisticated than that because when you take a limit, you see what depends on h is also what may depend on h also the prefactors may depend on h, but anyway the analysis that we did before is more essentially works. So there is a kind of, there can be a delicate question about coefficient, because for fixed coefficient it goes to 0, but in principle coefficients may also depend on choice of the step. But in any case, the coefficients, even they depend on the choice of the step, they at most power loss of j. So it doesn't matter which power law over j you put, because the lambda j will always win. Yeah, so it goes to 0 whatever the dependence of coefficients on j is. So this is of course stability. So this is certainly the condition that will guarantee that at least with a 0 right-hand side, everything works. So in principle, there is in principle, when there is a root with modulus 1 is also acceptable. Okay. Acceptable. And because, okay, it does not decrease, but it doesn't grow as well. So if the coefficient is getting smaller with age, then the whole stuff is decreasing. So in principle, we cannot rule out that lambda absolute value equal 1 is okay. So the right stability condition for which you can prove theorems, it combines all these properties. It also doesn't require that whenever absolute value is smaller than 1, it's okay that if they are not distinct. So there are two delicate questions. So first of all, when modulus of lambda 1 is smaller than 1, it's okay if all lambdas are not distinct, because you don't get the general solution in this form, but in slightly more developed form. So there appear extra. So if some lambdas are repeated, this is not general solution because there are not enough terms. But you can construct more terms which are called circular terms, which is a product of power laws by exponents. But it's okay. So the stability condition that we will not prove, but for you to remember. So you can just look at the book if you want to know the proof. So the stability condition is that it consists of two parts. So modulus of lambda is smaller or equal than 1 for all roots. So all roots should have this condition. And this is clear because if one of the roots has absolute value bigger than 1, then one of the terms explodes. So already with zero function, you don't have a correct solution. And the second condition is that if the absolute value is 1, then it cannot be repeated, right? Then lambda is simple. So there cannot be two equal roots which has absolute value 1. Because when you have two equal roots with absolute value 1, you get some extra terms which explode. Just they don't explode in such a violent exponential form, but they explode in the power law form. So there will be exploding terms. And that's it. So there is a theorem. I will not have to formulate, but anyway, so that's the book, the book that I mentioned. So what is the book? So it's Polish story. Introduction to numerical analysis. And this is paragraph 7 to 10, if you're interested to study details. Essentially, I just give an idea. So essentially, a multi-step method where f satisfies some regularity and consistency. Some regularity assumptions. multi-step method. Satisfying some consistency. And regularity assumptions. So I'm not making explicit, but essentially consistency, it has to do with the fact that this scheme is correctly approximating the step. Essentially that it's a higher, it is.
So is there any objectively good reason why we would use a multi-step method instead of a single-step method? Because it seems to be, there seem to be many downsides, right? And very few upsides, right?
Well, let's compare. There are many downsides in the analysis, but as soon as it works, downsides are over. You see, the downsides is more in the analysis and making sure it works. But as soon as it works, you gain in the you get the same order method with less computations. You see, because this is 4-order method just with single computation of the function f. With this, to have the same thing with the Runge-Kutta method, you will need four computations of function f. So that's if computing f is cheap, then it's okay. But if f is something very complicated and very costly to compute, then this method gives you just directly by computing f. You get one f, you get high order method. Just one computation, high order. And in principle, if you take larger k, you can get quite a high order method just by computing single function. So you just every step you can compute function once.
Right.
So that's a gain.
And intuitively, that's because I have already computed the function
In the previous points, yeah, you have more information.
Right, so
And you use this information, yeah. In single step, you just know at which point you arrived at the last time and disconsider the whole information before. And this information brings you information about derivative, second derivative, third derivative, and so on, if everything is regular. You know? And this is exactly this information which is used here by choosing the right coefficients, so that it cancels higher terms. So that's a point. But you can get instability. So this gives a whole analysis more complicated, but as I said, that analysis is complicated, but at the moment it works, it works. So you don't do this analysis in application. So you do this analysis just in order to create a routine. And if it's stable, it's stable.
The secret would be to choose some coefficients which would make your lambdas super, super small, and then they can basically hold up.
You see, you should take coefficient which gives lambda not small. It just should be not bigger than 1.
The smaller they are, the smaller the chance that age will force them out of the circle.
No, h will not. At least small h will certainly not force them out. Small h is okay. So the theorem gives. So let's formulate. So whenever you make a multi-step method satisfies the consistency, means that it's correctly represents the approximation. It's certain order bigger than 0. And the regularity is the assumption that is needed to prove the theorem. It's essentially some Lipschitz condition on f. So whenever you have these two conditions, then the method is convergent if and only if the stability condition is satisfied. So this stability condition. So all you need is that really that the left-hand side of this method should be all right. And you can just check it directly, because whenever you have a method, like we did with the two-step method, we take arbitrary function and then analyze all coefficients. And it turned out that if you want to make the best method, so just put highest order possible, then the left-hand side has eigenvalue -5, root -5. -5 means the system is unstable. Probably if you take slightly lower order, but choose coefficients in different way, you lose in order, but you can get the stability. Right. So that's the idea. So essentially it looks complicated, but not so much, because you do this job in order to check the order, but then you just should check that left-hand side has the right roots. And for analysis of PDEs, for schemes, it becomes slightly more complicated than that. But generally, the idea is the same. So the idea is that that there is a small addition which gives you the step, and the linear combination which is kind of the structure of the method. So this structure should not be unstable. So it should not create. It should not magnify errors by itself. So in particular, what you can see is that the single-step method. So let's say Euler method. So Euler method is what? Is y j plus 1 equal yj plus f tj yj h. Correct? So it's k equal one step, right? Which you just write as yj plus 1 minus, just put it on the left. So this is fj. Characteristic equation would be lambda minus 1 equals 0. So for Euler, you exactly get this lambda equal 1 case. But simple. Simple already because it's just one root. So you see this satisfies the theorem. So lambda, and you see the lambda 1 is important in the theorem because already Euler gives you lambda 1. So I guess lambda 1 will be always 1. Yeah, 1 is always a root because you see some of the coefficients should give 0. So 1 is always a root. So 1 is always a root, but it should not be multiple, right? So that's a point. So there should not be any root which has a absolute value 1, which would be multiple. Okay, so that's it. I think we should finish. So I'm not giving the proof because proof is rather complicated. Proof is complicated in this because we have to take into account these special cases when they're not distinct. Then there are some more terms. This goes back to this linear algebra when there are circular terms corresponding to multiple roots, and another issue is lambda 1, so also taking care of lambda 1. So that's a technicality to prove, but essentially it takes into account the central idea is that every term is exponential. As exponent, if lambda is smaller than 1, exponent goes to 0, is bigger than 1, it goes to infinity, and the only technicality is taking care of lambda equal 1. So that's a proof, and also, of course, taking care of the fact that this right-hand side will not lead to instability, which is this consistency and regularity assumption. So that's how you prove this text. So, but we will not do it here. So that's it. And so see you Friday, 244. So this is. I guess I don't need to send email anymore. Right? Everybody's here. Okay. Over Monday.